So our AC generator consists of a stator and a rotor, which rotates around in the middle, driven by our prime mover, typically a diesel engine. On the rotor, we have pairs of poles, okay, which are electromagnetic. Yeah? And these poles are driven past the fixed coils in the generator stator. Okay, and just as we've just seen, in doing that, we generate an EMF is induced in each stator winding, yeah, and the shape of the voltage which we create is sinusoidal. And there's a sine, okay. This is then taken out, and what we have, this goes through to our three-phase system, which we'll call red, yellow, blue. And what we create is what we call a line voltage. And in the case I'm going to do, the line voltage is 440 volts. Between there, and between there. So we've created our line voltage. The value of the EMF is based on something called the root mean square. But we don't need to go too much into that. But all we're interested in is the line voltage. So we're following Faraday's laws, producing this sinusoidal wave, which gives us our line voltage, which is a nominal, in the case I've mentioned, of 440 volts. Okay. Now, the next thing, how do we get that voltage that we require, 440 volts? Okay, so again, there are a couple of variables. The prime mover is turning at so many revs per minute, which we can equate to N, which is revs per second. So we can, once we know how fast the prime mover is moving, that's the diesel engine, the speed of which is controlled by the governor on the engine. That's rotating round, yes, and the size of the EMF is proportional to the number of revs per second and the value, the density of the flux. Just Faraday's law. Okay, so this little symbol here is the strength of the magnetic flux that we need in the generator to generate our EMF. Okay, and the value of this flux density in the rotor is controlled by a system called excitation. Okay, and we'll talk a little bit more about that as we go through the chat. Okay, so as well as controlling the line voltage, yeah, we also need to control the other variable that we've already mentioned to the surveyor, and that is the frequency of the system. European frequencies tend to be 50, American tends to be 60. Possibly 60 is probably a little bit more efficient, but that's by the by. So we need to control the frequency at which our generator works at. And the frequency, okay, is equal to, again, the speed of the prime mover in revs per second and the number of pairs of poles. Of pairs of poles on the rotor. Okay, so if we had a four pairs of poles motor and we wanted 60 hertz, we would find that the speed of the prime mover would be set at 900 revs per minute, whereas a 50 hertz system, again with four pairs of poles, that would be required to rotate at a constant 750 revs per minute. Don't worry about the sums, but that's just the way it works out. So the speed of the prime mover is controlled by the governor on the engine. Thus, by controlling the speed, we notice that this n, number of revs per second, is common to both the value of the EMF and the frequency. So thus, by controlling the speed and frequency, we can control the voltage output by varying the amount of flux in the rotor. So we want to vary the amount of flux that goes into the rotor. And this is done by something called the AVR, the automatic voltage regulator. A little bit more about that in a little while. Okay. A feature of AC systems is that they don't work, they're a bit more complicated than straight DC systems. So a feature of AC systems is that the voltage and the current generated are not always what we call in phase. Okay. Ship systems, the load that where all our electrical power goes to drive motors, heaters, lighting, etc. Everything we need electrical power for. Now in AC systems, they display different characteristics. We don't need to worry too much about it, but just know that wherever the power is being used, say in an electric motor, these motors are typically induction motors. So the characteristic is what we call an inductive load. Yeah. And what this means is that we have different types of circuits within the vessel. We can have inductive circuits, we have resistive circuits, such as heaters, and we can also have something called capacitive circuits, right? So what we get from this is it means that the voltage we generate, there's the voltage in our sinusoidal form. What this means is that for an inductive circuit, this voltage follows that pattern. But as we saw looking at Faraday, when we induce an EMF into a coil or a circuit, we also induce a current. Now, in our inductive circuit, the current that we generate within the circuit will lag, i.e. will be behind the voltage. And so if we start 0, 180 degrees, 360 degrees, it's gone through one cycle, we'll find that the current lags behind the voltage, like that. So inductive circuits have lag. We don't need to go into it, but resistive circuits, the voltage and the current are directly in phase. And with a capacitive circuit, we find that rather than the current lagging the voltage, the current leads the voltage. But don't get too involved with that. Right? So this leads to a general characteristic of AC systems where predominantly the system, the pattern is that the current generally lags behind because of the high inductive loads that we get within AC circuits. It lags the voltage. We give the angle of lag between the phase voltage and the phase current the symbol phi. Okay, it's just a Greek letter we use, and we'll see why that's important in a little while when we start looking at power factors. Okay, so if I was to don't to get too complicated, but if I show these voltage and this current rotating round in something we call a phasor diagram, yeah, we'll find that the voltage rotates that way, always rotates anti-clockwise, don't ask me why. There's the voltage, and for an inductive circuit or the general pattern of inductive loads, we find that the current will lag by this angle phi. Okay, so that's enough of it. And that leads us into the concept of power factors, which we will look at a little bit later in the chat. Ideally, when we look at power factors, we want to run our ship at as high a power factor as possible. The highest power factor you could get, which isn't actually achievable in practice, would be 1 or unity. Yeah, it's quite difficult to actually achieve unity power factor, but what we do need to ensure is that we run our electrical systems, our generation systems, at as high a power factor as we can. Typically 0.9 or slightly better. Yeah. And that could be running your electrical systems at a high power factor, could form part of your ship's energy efficiency management plan. Yeah. The reason is you will use less fuel, create less pollutants, and it's more economical. Okay.